Hi, my name is Brandon Edwards, and I work in Intel Labs doing research on security and privacy issues surrounding machine learning development and deployments. I am here to talk today about the Python open source framework, OpenFL. And I have provided some names here of other people at Intel that work on this project, including Micah Scheller, who is the lead researcher in Intel Labs on the project. So today, I'll start by giving a broad overview of federated learning. I'll then, and this will be the base, what I'll refer to as baseline federated learning, which is sort of federated learning in its basic definition. I'll then move to talk about some security and privacy threats that still exist for baseline federated learning and solutions to these threats. I'll then introduce OpenFL, which implements baseline federated learning, plus some of these solutions that I will refer to. I'll then talk about some research deployments that have used OpenFL, and then go over the high-level architecture of OpenFL and talk a little bit about what it takes to enter into it. So basic federated learning. Deep learning models generally require a lot of data and a lot of diverse data in order to generalize well when deployed to different locations where inferencing data would be located. One paradigm for training a machine learning model, given these restrictions, is to collect data from multiple entities and centralize it to a single server and then train the machine learning model there. And this I'll refer to as centralized learning. This can encounter some issues due to data privacy and therefore, and also due to, say, the capacity at that single or at that single location where you're trying to aggregate all of your data, as well as potentially data might be too large to transport, or the value could be too high, or potentially the value could be unknown to various collaborators, and so they may not want to contribute their data. So the alternative is federated learning. And here I describe, or I show a high-level workflow for federated learning, where I have 3 different data owners, which I'm calling collaborators A, B, and C. And here, instead of moving the data to a single server, we keep the data at the infrastructure where the data owners are and move the compute instead. So here we have each of collaborators A, B, and C will train a machine learning model, and will for, say, an epoch or two to obtain a model update. And then each of these collaborators will send their model update to the aggregator server, who will then aggregate the model to become the next consensus model that then gets redistributed back to the original collaborators, and that completes what we call one round of training. So this is iterated over for multiple rounds, and the final model then comes out of this process. In addition to these model updates in this diagram that could be sent by the individual collaborators, we can also have metrics be sent over, and that's common in the workflow for FL, so that all of the individual collaborators can, in addition, validate both the global model that they receive from the aggregator against their local validation data, as well as validate the local model updates that they compute before sending it over to the aggregation server. So just wanted to point out that I have in this diagram model updates being sent over, but as well, we can have validation metrics, and that's common. So there's a couple of ways in which FL model optimization is different than centralized learning. And these can be, excuse me, these can be, these can make the convergence properties for federated learning different than centralized. And in general, if the data is different enough across the different collaborators, it can be more difficult to get the model to converge. So I wanted to call out a couple of these. And the first one I wanted to talk about was in centralized learning, the batch draws that are made to apply to the model learning are done in a way that you have all the data located at a single location so you can shuffle it. And that means that when you draw your batches, you can do so in a way that the batch draws are independent and identically distributed. This is standard, but is not what we'll see in federated learning, because the training in federated learning is applied at the data owners. And so the batch draws in that situation will be dependent on the local data distributions that you have across each collaborator. So that's a difference. The second difference I wanted to call out was that in the case of centralized learning, model updates are applied after every single batch generally. So you take the gradients accumulated over a single batch and apply that to step the model in parameter space. This, in the case of federated learning, is also what's done for the local model update calculations. However, you have an additional averaging in the case of federated learning of all the local models when you go to send them to the aggregator. So this additional averaging doesn't happen in the centralized case and can make for different convergence properties. Again, this second issue is more pronounced. The more the data is different across the different collaborators, at the time the local models are averaged together, they could potentially have diverged quite a bit in parameter space. And so again, this is a problem that can be more pronounced the more the data is differently distributed across the collaborators. So these are things to be aware of. Federated learning does not have inherently the same convergence properties as centralized learning does, but we have observed in our experiments, one of these citations is from us, that that the federated model can match the performance of a centralized model, and others have observed this too. Though generally speaking, it is going to be slower to converge than in the centralized case. So now to talk about some security and privacy threats and solutions that exist for federated learning. Even though we're not sharing the raw data, we're still sharing model weights, and we still have a sharing of the compute that's performed during federated learning. And this is across collaborators that we may or may not trust, as well as the aggregator. All right, so I put these into two basic categories. One, threats due to the fact that we are sharing model weights. And then the second category, threats due to the fact that we have a sharing of compute. And in the first category, there's a couple of attacks that I call out here. The first is model inversion attacks, which are when an adversary would take the model and use it in an attempt to generate training data that was used to train the model itself. So I provide one reference here for a publication on that. The second is also similarly using the model in order to extract information about the training data, but in this case, it's a membership inference attack, which takes a sample of data and attempts to identify whether that sample was one of the training samples used to train that model originally. And so again, this is a situation where we are trying to get information about the training data used on the model itself. So the second category, again, as I said, is due to the fact that we're sharing the compute, and we have multiple collaborators performing training on the model. And one of the threats here is a poisoning attack, where training can be done in an adversarial manner in order to maliciously alter the model behavior. And this can take many different forms in terms of what the unwanted behavior could be. But an example could be, say, if this model is intended to be a malware classification model, and maybe an adversary is trying to get one specific malware binary to be not identified as malware for the model. And so that would be an example that we would call backdooring of the model in order to in order to have it infer and have the model inference come out in an adversary's advantage, given particular inputs or addition to particular inputs in general, or inclusions in that input of a key of some sort. So the other unwanted behavior that could be designed for during a poisoning attack could be actually, and this has been demonstrated in one of the publications I provide here, could be the incentive for the model to memorize more of its training data. This model poisoning can be done in such a way that you try to get the model to memorize more about the training data. And this would be model poisoning in support of one of these other attacks up here. And again, that's demonstrated in one of these citations. So solutions that I'm mentioning against these threats are in two categories here. One, the second category is algorithmic solutions, which I'll talk about, but the first is trusted execution environments. And I'm going to talk more detailed than only on this slide about trusted execution environments, but essentially they are hardware supported environments that allow for an application to run in a way that is that the data that's used during the application and even the code that's being used will be confidential to even privileged users on the system. And that can help against these threats, as I will talk about soon. The other category, as I said, are algorithmic solutions that can be included during federated learning. And these would be modifications of the workloads that are already run during federated learning towards additional security and privacy. So one example of this is robust aggregation. So the aggregation that is performed by the aggregator could be done so in a robust manner, robust to outliers, say. And this can, for example, help against the poisoning attacks, as sometimes the poisoning attack updates can be identified as outliers at times. So an example of this robust aggregation, this is really basic, but just a basic example would be to, instead of taking the average of all the updates, say per parameter, take the median instead. And so that's just to give an idea of how a different type of aggregation could be robust to outliers. So another algorithmic solution is differentially private training optimization. And this is a replacement for the training work that is performed. And this specific replacement is the addition of noise during training in order to obfuscate or in order to reduce the influence during training of individual training samples. So in this case, we have that the output of training, due to the addition of noise, is going to be less sensitive to just single samples of training data. And what comes out of this is a guarantee in terms of a type of basically likelihood that that the particular model that you got out of the training pipeline will be dependent upon a single sample of data, of training data. And this type of training that reduces the dependency on single samples is inherently helps in both this of the two model leakage attacks that I talked about previously. So there are a number of other algorithmic solutions that could exist here, but I mentioned a few. All right, so now on to the framework OpenFL and what it provides for us, which is essentially baseline federated learning plus the addition of trusted execution and algorithmic solutions to security and privacy. So OpenFL here, I have provided a couple of links, one to OpenFL on GitHub and the other to a white paper on arXiv. And one thing I wanted to call out immediately is that OpenFL, a relatively recent release, 1.3, now does run inside trusted execution environments using Intel SGX. Okay, and a little bit more about trusted execution environments at a high level. So they provide for confidentiality and integrity and attestation during the workload that while the workload is being while the workload application is being run inside the enclave. So the confidentiality is essentially that while the workload is running, the data that it's computing on, as well as the process itself, cannot be inspected by even privileged users on the system. This can provide for a couple of protections. One is protection of the model IP itself, so that if everyone, all of the nodes inside a federation are running inside trusted execution environments, then the model itself does not need to be exposed until the exposure of the model is essentially controlled by the application itself, and the aggregator process, all of the individual collaborator training processes can be running inside enclaves, so that even, as I said, privileged users at any of those systems cannot inspect that model while it's being computed on. In addition, confidentiality generally helps because that model is, because it's possible to not allow access to that model. And again, the application is the one that ultimately controls that. The trusted execution environment itself allows for that no one can inspect the data being processed, or and including the model, but the application will control, and that is to say, how any modifications you do to the OpenFL code would control when the model is finally released. And so in this setting, it takes what otherwise would be open box attacks, meaning that the adversary has access to the model weights and can perform whatever compute that they want on that model in order to attempt to, say, extract information from it about the training data. And it turns those into closed box threats. And specifically, the access that an adversary will have to the model, and this could be in terms of actually receiving the model weights, or in terms of being able to get validation scores out of that model, etc. These are all controlled by the application, in this case, OpenFL would generally would allow the aggregator to see validation outputs, and that's it. Okay. Sorry, and the collaborators themselves could receive those could receive validation results according to how it's the federation is configured. So in addition, we have integrity and attestation. Integrity being that we're saying that the workflow that we inspect the code that's going to be run during the federated learning process, and the presence of trust execution environments will assure us that that code is exactly the code that's going to be run. It uses hashes of the code in order to make sure that the code that you previously inspected is precisely what code is running in those trust execution environments. And in addition, there's the ability for remote attestation where, say, the collaborator, before communicating with the aggregator, as part of that protocol, as part of the federated learning protocol, will ensure that the aggregator is indeed running inside a trusted execution environment, so that that they can trust that they can go ahead and communicate with that aggregator. So this, in general, will ensure that only approved models and training procedures are run, and that that it protects the execution of the algorithmic defenses that we had discussed previously. So just generally speaking, trusted execution with Intel SGX will help protect the private assets and also help protect the integrity of the intended workflow. Okay, so I wanted to discuss a couple of research deployments that have used OpenFL. Just as examples of real-world use of the OpenFL framework. And the first is for federated brain tumor edge detection. Intel, along with the University of Pennsylvania Perelman School of Medicine and 70 other research medical institutions, performed federated learning in order to train a brain tumor edge detection model. This was geographically, it was a global effort. It was done across 6 continents. The data was comprised of over 6,000 full brain MRI scans. And that was over 5 terabytes of data in total. That's including the training data as well as the validation data and the test data. And in the end, it was demonstrated that there was a 33% improvement in the final consensus model coming out of federated learning. Improvement in locating the operable portion of the tumor, which is one of the most, which is an important task of the tumor location. And this is comparison over a model that was trained on the public data set that's common for this use case. All right, another was a COVID-19 use case. This is with the Montefiore Health System. And in this case, federated learning was performed over that Montefiore Health System's infrastructure. This is a large integrated care delivery system in New York, comprised of 11 hospitals distributed across poor and affluent areas. The task in this case was in ICU, prediction of acute respiratory disease or death. And in this case, the resulting model was integrated into the health system workflow, and it helps to identify high-risk patients before an irreversible terminal event. Excuse me. So and based on the success of this, OpenFL is now a core component of the Montefiore Health System AI ML infrastructure. And the last example I'd like to provide was for astronaut health, and actually NASA, the Mayo Clinic, NASA Gene Lab and other organizations perform federated learning in order to attempt to identify which genes would be most affected by radiation in space. So in this case, there was a causal model that was being trained, and FL was performed across multiple data sites. Some of them contained human mRNA data, and some of them contained mouse mRNA data. And in this case, there was federated learning along with the additional complexity here of some of the data being mouse and some being human at the various sites. And one of the outcomes of this project was the identification of a gene previously only known to be associated with arthritis, but now that is identified as one that is related to the effect of radiation in space. Okay, so finally, I wanted to talk a little bit about the high-level architecture of OpenFL and getting started, sort of, where code would go. So here is, as I said, the high-level architecture of OpenFL with some color codes. Blue is the OpenFL code. Black is third-party code. Green is are files that are produced by the FL code itself, and the orange is the color that indicates the user pieces, and so these would be the locations where, if you come to OpenFL with a new use case, where you will be bringing some of the code that you have from your initial experimentations with that use case. And there are three different categories that are provided here in the diagram. FL plans, which I'll talk a little bit about, which essentially describe the configuration or the configuration file for the federated training. And then ML models and dataset code, which go into what here is indicated as the FL plan executor, sorry, I'll say. And that is also what we would call a task runner. Okay, but again, these orange portions indicate where, if you had already done some experimentation in a centralized setting with the particular use case you're bringing to OpenFL, this is where your code would come in. So there are, that's what I'm providing here for focus. There are other modifications that could be made against the default workflow that is carried out in OpenFL. And those, some of those would also be made in the FL plan, and some could be modifications elsewhere. The standard workflow that OpenFL carries out is essentially what I've described so far, which with a little bit more detail, I'll say is that say a percentage of the collaborators, there's a certain percentage that's identified of random selection of collaborators that will perform the training each round. And each round, then each of those collaborators receives the global model, validates it, trains on top of that global model using their local data to get their local model update, then validates that local model update against their validation data, and finally sends it to the aggregator to be aggregated. Those that is the basic workflow. If there are additional tasks that are desired at the collaborator ends, if the aggregation that's performed is is custom in some way, then those would be modifications that would um, be made in other locations of the code, other than in the orange portions that I'm describing, and that can certainly be done. Um, but is just in a different location, or that's it. Would be a little bit different. It'd be more than what I'm describing here. And so let me talk more about these modifications that would be made in terms of the model and the data set. So generally speaking, as I was saying before, the understanding is that when you come to federated learning with a new use case, what makes sense is that you've done a little bit of experimentation first with, say, a small data set or a public data set in order to understand the use case before you try to federate. And these initial exploration activities would provide for you information about what data preparation is appropriate, what model type, what architecture, what are the hyperparameters that appear to be good in this use case against that model when training. And then for that choice of architecture and hyperparameters, what are the convergence properties? How quickly do we see it converging? So these types of explorations usually provide a bit of code that you have. So you've determined what kind of data preparation. So you have a specific data loader that you've implemented, and so forth. You've picked, PyTorch or TensorFlow or some particular DNN framework. When going to use OpenFL, then that code that you bring from that initial exploration will go into the model data loader and task logic code, which goes into the class that is the task runner class in OpenFL. That is the plan executor that I was talking about before. And this is one of the classes that is pointed to in that is referenced in the FL plan. The FL plan specifies generally a number of things about the federation, and what this FL plan includes is in one case are pointers to the relevant Python classes that will be used for this federation, and the initialization parameters for each. So some of the classes that are relevant I call out here, and one I just referred to, the class to run the collaborator tasks, or the task runner. And this is where the model data loader code, as well as the specific logic of how training and validation will be performed, goes. This is one of the classes. Another class that is important in terms of what we've been discussing is a class to assign tasks. And this is the class that would have the functionality, that has the functionality to, say, select a random percentage of collaborators each round in order to train. It also determines, it also is the class that actually assigns the tasks themselves. And so the specific tasks and the order of those tasks come from the FL plan itself. As well, the FL plan contains, as I said, the collaborator tasks to perform each round, and the percentage of collaborators to choose each round, and other things on top of that, but I'm providing a few here. So for the customization, there are some base classes examples that are provided in OpenFL for PyTorch and TensorFlow that demonstrate examples of task runners. And in many cases, these are sufficient. You can either inherit from them and override some of the attributes in order to define your specific architecture. Or you can use them as a template and just write another class yourself. But in these cases, as I said, the model architecture definition can be dropped in, the specific metrics that are going to be used for training and validation, as well as data augmentations that are specific to your use case. All of these things can be incorporated here. Okay, and that's it. With that, I will say thank you. And I have here at the end, again, the 2 links, one to the GitHub code and one to the white paper on archive.
Okay, all right, thank you, Dr. Edward. Okay, any questions? See if I have any questions in the chat.
Okay.
Okay. So maybe I can ask a couple of questions. So I think there's a couple of, framework can do better learning, right? So OpenFL is one of them. So I think maybe can you explain a little bit, I think a lot of students, they, when they write a paper, do some research, they want to, compare with some existing algorithm, right? So if you're doing better learning, let's say I want to address the client drift problem, I want to compare with, Fed proxy or scaffold. So are those kind of, like a well-known baseline algorithms have been already implemented in OpenFL, so they can easily, just do the run experiment they can and just do the comparison with those existing algorithms.
Right. Thank you for the question. I would say that some of those will be implemented in OpenFL. We are actively developing on a regular basis in order to incorporate more new algorithms, and we definitely identify that as a big need to be able to have, what are the standard state-of-the-art algorithms out there incorporated into the framework. And so I would say this is a big effort to do so, to include all of those, and some of them certainly are, but the effort is ongoing.
Okay. So since this is a computer vision conference, I want to ask, so is there any, support specific for the vision task? Like if I want to do face recognition or maybe video analytics, like action recognition, action detection, will be any of those kind of support or libraries built, maybe not right now or in the future, considered to incorporate in this OpenFL framework?
Yeah, so first of all, OpenFL is designed to be use case agnostic. So the OpenFL framework itself is not designed to incorporate in the framework itself specific use cases. However, the examples that are included in OpenFL, I would say a high percentage of them are vision use cases. And as you saw, one of the biggest use cases one of the biggest efforts that was undertaken with OpenFL was this brain tumor segmentation task. And that was, as I said, done in collaboration with the University of Pennsylvania Perelman School of Medicine, and their framework, FETS, Federated Tumor Segmentation, has many tools that support the task of segmentation on MRI scans, for example. So that's a separate framework that but is one of the examples that we have for OpenFL. So I would say, again, generally speaking, domain specific code is not part of the OpenFL framework itself, but we have many collaborations with experts in various fields that helps us to include as examples in the framework some of these workloads. And if there are questions with respect to getting into some of those use cases, we would be happy to discuss those with people.
Okay. Okay. Awesome. Thank you. So I
Yep.
think there's a question in the audience.
Okay.
Do you mind come to the microphone? So thank you.
Yeah, thank you for the nice talk. I'm no expert in federated learning, but I found it interesting that after having received the aggregated model weights, the collaborators seem to run a validation procedure essentially. So I would like to know what happens if one of them says, okay, this model is not so good.
I'm sorry, the audio is really bad. So if you could either repeat the question or, I'm sorry, I'm not catching
Yeah,
it.
maybe come here. Yeah. Could you please come here? Yeah. Thank you.
Thank you. Sorry.
Okay, maybe now you can understand me better.
Yes.
Yes,
okay. Thank you. Thank you.
Yeah, thank you for your nice talk. So I would like to know about the aggregated model weights. So upon reception of these from the collaborators, I understood you that each of the collaborators runs a validation procedure decentrally. And I would like to know what happens if one of them says, okay, this was a fail, and the others say this is a pass. So is the common model then rejected, or what are the typical measures in federated learning?
Right. Okay, great. Thank you for the question. This is something that we've been thinking a lot about. So far, right now, there are not procedures in OpenFL to perform this type of filtering or handling of, shall we say, low validation scores or indications through the validation scores that there may be a problem. So far, we have been handling that manually. But there's a bit, but we, and particularly during the example of the brain tumor segmentation with the University of Pennsylvania and all those other collaborating institutions, we were able to identify via the validation scores when there were some really critical issues. We saw some poor validation scores, notified the institutions, and they inspected the data and they found some issue and corrected it. And so we've gone through those sorts of processes manually in the past and have been gathering our learning. And actually, there's a big effort to incorporate now into OpenFL a governance solution that will handle such things as you describe automatically, in addition to such things as registration of data sets, code review and acceptance of an FL plan for a particular FL run, handling of the PKI that will be used for all of the different members of the Federation. All these sorts of governance activities are really critical, particularly when you're dealing with a lot of institutions that you're trying to perform federated learning across. And so we identify this as a need, but as I said, it's an ongoing effort. And right now, this is functionality that is being developed into OpenFL.
Okay, thank you very much.
Thank you for the question.
Okay. Okay, so Dr. Edward, there's a question in the chat. So do you have any examples when OpenFL is used for edge device, IoT scenarios?
We're looking at such use cases. But no, I don't have any to report on at this time.
Okay.
Yeah.
So I would say in this case, like if want to deploy OpenFL like on like Jetson Nano or Xavier. So right now OpenFL is not supported on this kind of edge device. Is that what you're saying?
As far as deployment and infrastructure, I am not as familiar with those details, to be honest. For example, the two technologies that you just described, I'm not familiar with.
Okay. Okay.
Yeah, I'm sorry.
Yeah, but I think maybe we, think we can check the GitHub repo and also the papers and see if there's any details.
Yes, thank you.
Specific for
Yeah.
the edge computing scenario. Okay,
Right.
great. Any other?
Yeah, and there's, sorry, I would like to say there are others on the team that would have expertise in that, certainly. As
Yeah. So is there like a community for OpenFL, like people can, ask questions or maybe seeking help if, for,
certainly, yeah, I would go on the GitHub and file, and there's a discussion forum, and as well as issue filing and all those sorts of
Okay.
things. Yeah, we really welcome people to participate.
Okay, awesome. All right. Is there any other questions, audience?